We go to the second case where at a time t0 we have p0 parent atoms and we have d0 daughter atoms. Okay, this is at initial time. At a time t, p0, you know, we have the indicate atoms will decay to stable atom. So p0 at a time t equals to pt indicate atom plus dt of stable atom produced by decay. And the total number of stable atom at a time t equals to the initial number plus the produced number. Okay, let's start to calculate each term. We have p0, we can start with this one. P0 equals to pt plus dt star, and we can calculate dt star equals to p0 minus pt. What is the value of pt? Anyway, here I want to calculate p0. Just I want to simplify the relation to find finally this expression. Okay? Anyway, p0, we can take the decay's law. Pt equals to p0 exponential minus lambda t. P0 equals to pt divided by exponential minus lambda t. We can put the exponential up, we change the sign to get finally p0 equals to pt exponential lambda t. We put p0 by its value here to get dt star, the produced stable atoms, equals to pt exponential lambda t minus pt. This one minus this one. We take a common factor dt exponential lambda t minus 1. Okay. Also, we take now this relation dt equals to d0 plus the calculated value dt star. We get finally this relation. Simply, it's a relation between the number of stable atom at a time t and the now equals to the initial number of stable atoms plus the number of indicate atoms exponential lambda t minus 1. Here, this equation is called Isochrone Equation. Okay? Isochrone Equation. At this point, as you know, in general, we can calculate dt and pt by mass spectrometer, but we don't have any idea about the initial value of stable atoms. Okay, so in this case, we have to follow a method to calculate d0. How can we calculate it? Here, now, first of all, if I give you, for example, one parent atom and one stable atom, we can take a system of rubidium and strontium. Like in the case of carbon, we take a ratio of carbon 14 and carbon 12. Here also we have to take a ratio between one stable atom and one indicate atom. So we take as a stable atom strontium 87 and as a radioactive atom rubidium 87. It's a system in the case of D0 and P0 at initial time. We can apply the Isochrone equation. In this case, Rb is a parent atom, P, T. We can substitute its value here to get here. We put RB87 and dt and d0 is the number of strontium at a time t and the number of strontium at initial time. So we can put here strontium at a time t and strontium at initial time. And we put here exponential lambda t minus 1, lambda t minus 1. So here we apply Isochrone equation in the case of a system of rubidium and strontium. Here, as you see, we have rubidium as parent and strontium 87 as daughter. And we have lambda of rubidium equals to 1.42 times 10 power minus 11 years minus 1. And we have T half. As you know, we don't have the initial value of daughter atoms. Okay, we don't have its value. What is the method? Here we have to find, in general, I tell you, we have to find another stable isotope with strontium. We have strontium 87. This value of strontium 87 will increase with the time because the disintegration of rubidium. We have to find another isotope Sr87. This isotope is a stable isotope and doesn't change through time. It means its value at T0 and at T will be the same. Okay, so here we go to divide the Isochrone equation by this quantity, strontium 86. So as you see, we have the Isochrone equation. We divide strontium, we divide all the equation by strontium 86. As you see here we don't have a time t or time t0. The number of strontium 86 is the same at time 0 and at time t. Okay. Here we write again Isochrone equation. This term strontium 87 to strontium 86 at a time t and rubidium 87 to strontium 86 at a time t, we can calculate these values by a mass spectrometer. Okay, it's easy. You have a spectrometer, a detector. We can capture the emission of strontium 87 and not emission. We can calculate the mass of these terms. So it's easy to calculate them. We will talk about mass spectrometer in the last chapter. Okay, how this device can work to determine the mass of any matter, any element. Anyway, so we have only this value, strontium 87 to strontium 86. In general, strontium 87 at initial time, we don't have its value. Okay, here, if you look well, the Isochrone equation, it's similar to y equals to b plus mx. It's the equation of, it's a linear equation. It's a form of linear equation where we can plot y in terms of x. We get the a line where the slope of this line equals to m, equals to exponential lambda t minus 1. This is the slope of this line. In general, I give you this value and this value. Okay, so the slope of this line will be exponential lambda t minus 1. This is the slope. And from this equation, we can find the time t or the age of rocks and fossils, where lambda t equals to ln slope plus 1, t equals to ln slope plus 1 divided by lambda. So in general, I can give you, for example, the value of strontium 87 divided by 86. I can give you also rubidium 87 divided by 86. You can draw a line and you find the slope. When you find the slope and you have the value of lambda of rubidium, you can calculate the age of this matter. Okay? Or let's go back to the Isochrone equation. So the slope equals to E lambda t minus 1. You know lambda is a small value. We have a value times 10 power minus 11. Okay, because lambda equals to 1 divided by half time. In general, lambda is a small value. To simplify the relation, we can say E lambda t minus 1 equals to lambda t. So we can substitute its value here. We get here this value, the Isochrone equation. We can calculate t to get finally this relation. In general, here you have to simplify all these calculations by Isochrone equation. First of all, if I give you a problem with one stable atom like strontium, maybe you can have another maybe lead Pb 207, Pb 206, any stable atom, one stable atom and one undecayed atom like rubidium or uranium. You can follow this procedure to calculate the time. You can calculate the Isochrone equation, and you have to find another isotope, stable isotope, and you divide all the equation by this quantity of a stable atom. And you can draw xy to find the slope, or I can give you the value of the slope directly. You can apply the equation t equals to half equals to 1 over lambda times exponential times ln slope plus 1. Okay. The same equation, what is the difference between this case, case 2, and case 1? Only in the case 2, we have D0, we have a quantity of stable atom at initially. Okay, so if I eliminate the initial value of strontium here, we must get the same value as before. Okay, look here at if no daughter element, no daughter atoms, we can say atoms, no daughter atoms at T0, so we can eliminate this one. So we get this new equation. We can eliminate the same term of strontium 86. We get this relation, which is equal to the daughter divided by parent equals to the exponential lambda t minus 1. It's the same expression in the case as in the case 1, where we don't have any stable atom at T0. And the same, we calculate the value of T. So here we can say as a general equation, we have Isochrone equation. If we have one decayed, one stable atom, and one unstable atom, the general equation is the Isochrone equation. If we have D0, you can follow this equation. If you don't have it, you get the initial result of time. Now, if I give you, I want to complicate a little the problem. If I give you two unstable atom and two stable atom, two undecayed atoms and two stable atoms, what can we do? Here, in this case, look, I give you, for example, one parent atom, uranium 238, will decay to lead 206. So we have one parent and one daughter, okay? And we have another parent atom 235 of uranium will decay to lead 207. So we have here two isochrone equations. We can follow the same for one parent, one daughter to get one isochrone, and one parent, one daughter to get another isochrone equation. But be careful, we have to find another stable isotope. Here it will be Pb 204, like in the case of strontium 87 and 86. We found strontium 86 as a stable atom isotope. Here, Pb 207, 204. We take the same equation, Isochrone equation, and we divide. Here, first of all, we have uranium 238 and Pb 206 as a stable atom. We write Isochrone equation and we divide by Pb 204. Here I have a mistake. We don't have T0. We don't have T because the number of Pb is the same at a time T and at a time T0. Okay? We can follow the same Isochrone equation for uranium 235 and 207 of Pb. We write the Isochrone equation and we divide all the equation by Pb 204. So here we have two equations, two Isochrone equations. What we can do, in general, if we have two parents and two daughter atoms, in this case, I simplify the situation where I tell you no daughter element, no daughter atoms at T0. Just to simplify, in general, I cannot complicate the situation. We don't have any daughter, just I give you two parents atom and two daughter atoms without initial stable atom at T0. So in this case, if you come back to the equation, as we don't have initial lead 206 and we don't have initial lead 207, we can eliminate this one and this one. So we get simply new isochrone equation will be this one and this one. So also we can eliminate this term with this term, also this one and this one. We get finally these two equations. It's the same equations like the first case, okay? Here we can divide this one by this one to get finally a relation between the two parent atoms and two undecayed atoms. This equation is called Concordia equation between uranium and lead. So let me resume the situation. First of all, to determine the age, you know, in the case of organic matter, you have to follow simply the decay's law. We can take two isotopes, carbon 14 and carbon 12, and we can find the age simply. In the case of D0 equal to 0 at initial time, we get a relation between the parent and the daughter atoms. D divided by P equals to the exponential lambda T minus 1. And you can find T. In this case, if you have only one parent and one daughter, you can follow directly these equations. Okay, you can put the number of daughter, the number of parent directly, and you can calculate the time. But I advise you to find this expression. Don't write it directly. Write the equation, the case law, and calculate them. You have to prove this expression. In the second case, where at T0 we have D0 and P0, here you have to write the Isochrone equation. You have two cases. If I give you one isotope, one stable atom, and one indicate atom, you can find this one. If I give you two unstable atoms and two stable atoms, you can follow the Concordia equation. Okay, like this, you know exactly the problem, which equation can you use for each case. Okay, in the next video I will do some application, and we go directly to the artificial radioactivity. Now, when we have a spontaneous decay, in this case, we have a natural radioactivity. But in the other case, in the next video, we have to talk about the artificial radioactivity, where we can create a radioactive element, and we have to do some application in the next video.